In the last lecture, we talked about simultaneous equation, and now we will continue that, and we will extend the simultaneous equation to the form in the first order, which is of the form p1 dx plus q1 dy plus r1 dz, which are in three variables x, y, and z, and are of first order. This is equal to 0, and the second equation p2 dx plus q2 dy plus r2 dz equals 0. So a simultaneous equation of the form this type. So how to solve these things? Let's recall what we have learned in high school. So if we have x plus y plus z equals 0, or say x1 y1 z1, and x2 plus y2 plus z2 equals 0, or say they have a coefficient a, b, c, d, e, f, and if we want to find out in their ratio, like x divided by, then which is equal to y divided by, and is equal to z divided by. So we used to take, when we are going to find out what should be in the numerator of x, the denominator of x here, we will exclude the x coefficient. This part we will exclude, and this y and z coefficient we will cross multiply, right? We'll cross multiply, which would be bf minus ec. And if we want to find out what should be in the denominator of this y, then we will eliminate this coefficient of y and cross multiply the others. So just like that we used to find out. And now also we would do just the same, but now we are talking about the coefficients of the derivatives. So here we want to find out what should be in the denominator of dx, dy, and dz, just like that type. So after finding out, we should have here dx divided by q1 r2 minus q2 r1, which is equal to dy divided by r1 p2 minus p1 r2 equal to dz divided by p1 q2 minus q1 p2. Right, so we got those, and we will write, instead of this denominators, we will write just p instead of this, and q instead of this, and r instead of this. So after writing those things, we will get dx by p equals dy by q equals dz by r. So we have this kind of equation, and this is very easy to solve, this kind of things. So there are two methods, in which the first method might be you will take just the two of this, or maybe this part, or the first one and the last part, then we can integrate after simplifying, of course. And it is easy. I hope it would be more easier for you to catch up with this by seeing an example. All right, let's see one simple example, which is to solve a simultaneous differential equation of the form dx by x equals dy by y equals dz by z. So suppose the question gave us this, and how to find out? We can take all of them, or we can take just the two. So let's take these two in the first, So we will get dx by x equals dy by y, right? So if we integrate this, integrating, we will get log of x is equal to log of y, and then the integration constant, which we can write log of c1. All right, let's write log of c1. So we will get x is equal to c1y, right? By applying the properties of logarithm, we will have this log y plus log c1 is equal to log of c1y, right? So this part here is log of x, so log cancel each other, and we will get x equals c1y, this part. So this is the first case, and then we can take another. So we can take the last two terms, which is dy by y equals dz by z. So we will find out the solution for this by integrating. Then we will get this log of y is equal to log of z plus log of c2, maybe, let's say. So what we get is y equals c2z, right? Just like before. So those equations, for example here y equals c2z and here x equals c1y, those two are the required solution. All right, we have two solutions, which is x and y. So x value is c1y and y is c2z. And from this, if we want, then we can find out what would be the value of z also, right? Substituting the required ones. So that would be all. That is very easy to find out and very easy to solve this kind of simultaneous differential equation. Okay, now let's see one example which is more complicated than the first one. So let's say our question is to solve dx by yz equals dy by zx equals dz by xy. All right, so it seems complicated, more complicated, right? But this is not that complicated. So let's see here. We can take the first two terms. So what we get is dx by yz equals dy by xz, right? Zx. So here the z term can cancel each other, so it wouldn't be there. So we have this, and this one we can write x dx equals y dy, right? So if we integrate this, so we can have x squared divided by 2 equals y squared divided by 2 plus, let's call it c naught, the integration constant. So this one, if we multiply it by 2, the whole term, so we get x squared and y squared, let's take it in the left hand side, so minus y squared equals 2c naught, right? 2c naught. So we can say that this 2c naught, we can denote it by another constant, say c1. So c1 is nothing, just 2c naught. Okay, instead of writing 2c naught, we just write c1, which are just the same. All right, that is the first case. And we have the variable z also, so we have to include one solution which contains the variable z. So we have to find another one. So let's take from our equation. What should we take? Let's take the last two terms. All right, let's take the last two terms, which is dy by zx equals dz by xy. So here x can cancel each other, they can cancel out. So if we rearrange this, we can get y dy equals z dz, and we can integrate them. So by integrating, we will get y squared by 2 equals z squared by 2 plus, let's call it now c Okay, C3. All right, let's call it C3. Then after simplifying, multiplying all the terms by 2, we get y squared and z squared if we get it on the other side. So minus z squared equals 2C3, right? But this 2C3, let's write it as C2. C2, where C2 is nothing, just 2C3. Okay, so y squared minus z squared equal to C2, and y squared x squared minus y squared equals C1 are our two solutions. The required solution are these two. So that is all how to solve this type of simultaneous differential equation, and it's not that difficult, and we might find some examples difficult, but we can try it out, and the method are just the same, the process is just the same. Now let's go to another topic, which is total differential equation. Total differential equation. What are total differential equation? Is that a differential equation which are of the form, right? An equation of the form p dx plus q dy plus r dz equals 0, where p, q are functions of x, y, and z variables, and these are called the total differential equation in 3 variables. What are the 3 variables? X, y, and z are the 3 variables. All right. So to solve this, we have to have condition of integrability, because some part may not be integrable. For example, let's see here. Suppose our p is just 1 and q is just 1 also, and our r is say x. All right, dz, because p, q, r can be functions of x, y, and z. So here dx and dy might be integrable, but this part is not integrable now. All right, so we have to have some condition of integrability. So that means this whole thing is not integrable. So to solve this total differential equation, we have to integrate them. So we have to have a condition of integrability, and that condition of integrability, we will not put some a proof here. If you want a proof, then you can look at the books, and we will just write what is, right? What is that condition? So the condition here, I'll just write here. So the condition is we take p and take a partial derivative of q with respect to z minus the same one r with respect to y plus q r with respect to x minus p with respect to z plus r p with respect to y minus q with respect to x has to be 0. So this sum has to be 0. So if this is 0, then that means the equation is integrable. So this is the condition for integrability, and we can write this equation in matrix form also, which might be sometimes easier to solve. So in matrix form we can write here PQR, then here del x, del y, del z, which has to be 0. All right, so this is in matrix form. So let's see one example which is very easy. Let's see an example here. So example is to solve the differential equation, the equation y plus z dx plus dy plus dz is 0. So here this is our p, then this is q, which is 1, and r is 1 also. So we can write p is y plus z, and Q is 1 and R is 1. All right, so let's have the condition. Is it integrable? Is it integrable? So what is the condition for integrability? The condition for integrability is we can use the matrix form, or we can use this very long one. So Q and R are 1, so that means they are constant, right? They are constant, so this part would be 0 because they are constant, and the differentiation of constant functions is 0, and this part is 0, this part is again 0, and Q and R are 1, and P is y plus z, so this whole part is 0, right? This whole part is 0. And P, if you differentiate with respect to y, then it becomes 1. And if we differentiate with respect to z also, it becomes 1. So here is minus 1 and here is plus 1. Here it would be plus 1, and here it would be minus 1 because of this sign. So that means minus 1 plus 1 is 0. So the condition is satisfied. Alright, the condition is satisfied. So our equation is integrable. So if it is integrable, we can write y plus z dx plus dy plus dz is equal to 0. So we know that it is integrable, so we can integrate it somehow. So we can divide the whole term by y plus z. So if we do that, plus dy plus dz by y plus z, right? Because dy by y plus z plus dz by y plus z, if we take the LCM, then we will get just this. Then we can integrate, right? We can integrate. So if we integrate this and this, then here we can get x, just x, plus, so dy plus dz by y plus z. One condition is if you differentiate the denominator, and if you get the numerator, then you can take log of the denominator as the integral. So that means if you integrate y, then it is just 1, and z just 1. And also if we differentiate y, we can get dy, and if you differentiate z, we can get dz, right? So that is just the case. So we can write this integral part as log of y plus z equals, let's take c, but since we have log here, so we can take log c also. And x, how can we write x here? Is that okay, e power log of x, then e log would be cancelling it out each other, right? So it would be just x, but we want log in the base, so log of e power of x, so it would be just x also, plus log of y plus z equals log of c. Right, so log, if you sum up, then you can take the product, so log of ex into y plus z equals log of c, and you can cancel out log, then we can get ex y plus z equals c. So that is our answer. That is the final answer. It is very straightforward, and you can apply the condition for integrability, and if it is satisfied, then you can just integrate them by simplifying them, of course. First, you can simplify them. If it is not integrable, then you cannot integrate even if you rearrange, right? So if you know that the condition for integrability is satisfied, then you know that you can rearrange the terms, the coefficients in some way to integrate them and get the answer. So this is how we do. And there are some formulas for the integral of those things. So those are given in the books. your referred books and that you can see. So I think that is enough to solve another some examples. You can do it on your own now. So I'll write 2 examples here which you have to solve. So the first one is that simultaneous equation. So you have to solve it just like we solved in the first case. And let's see, solve this. Dx by y squared equals dy by x squared equals dz by x squared y squared z squared. All right, so this is the first question. And the second question is you can solve yz dx plus x squared y minus zx dy plus x squared z minus xy dz equals 0. So this is total differential equation. So these 2 parts we have done in this lecture. So I hope you can do it. And if there is any doubt or any questions that you cannot solve or do not know how to proceed further, then you can also always drop your question. All right, so that would be all for this lecture.